In that very first video, we showed that the Rev F production board has 103 chips and pretty much settled that the prototype had only 45.
And all that, and Atari was getting tired of their engineers designing games with 150 chips, 160 chips, and 190 chips, and I did all our breakout in 45 chips. If it's under 50 chips, we get this amount of money, and if it's under 40 chips, we get more. We get 700 if it's under 50. We get 1,000 if it's under 40 chips. So he was trying to pressure me to save a few more chips. You know, I got it down to 42, but then it went back up to 45 by the time we got it working.
That's a pretty big difference in chip counts, but a lot needed to be done to turn the prototype into a reproducible, marketable product. In this video, we'll try to reconcile the difference by removing stuff to get as close to the prototype count as possible. There's general agreement that the prototype was only a single player, had no sound, no flip screen, no coinage support, no bonus logic, and no second wall of bricks. But there is some disagreement about scoring being in the prototype, and if so, was it on screen or off board on some LED display. For example, in an article in the Atari Archives, Kevin Bunch writes that Wozniak dropped on-screen scoring for an LED panel. In a separate Atari Archives video, the narrator states that the prototype was missing full scoring, whatever that means. In an interview with Atari historian Martin Goldberg, Gary Waters, who you all know did the production engineering, said that the prototype had no scorekeeping, which I think would be a highly reliable statement. But on many occasions, the Woz himself alludes to scoring being in there, and I think he would know his own work. Now we can't just start yanking chips out of the production version because there are many shared gates, so we'll start this adventure on paper. Please also realize that much of this is conjecture, so don't take it as gospel. I'm just sharing my thoughts, and I made a lot of assumptions. For example, if you're going for low chip count for a high bonus, you're not going to do the fancy stuff. So I assume the following: that there was only one speed for X and Y motion, so no need for a volley counter or a speed up logic. That there was only one Y deflection angle instead of varying angles depending on where the ball hit the paddle, whose size didn't change. And there was only 1 point for every brick, assuming there was scoring. Let's start out with a list of equivalent chips from each area based on gate consumption using the convenient retro-schematic sectioning. The oscillator section, for example, consumes one 74161, 1/2 of a 7404, and 1/4 of a 7437, so its equivalent chip count is 1.75. Moving down the list, the video counters take 4.83 chips. The video sync section takes 2.25, and so on. In total, you can see that the production Rev F version has the proper 103 total chips. Let's whack the easy stuff first. We can completely remove the flip screen circuit, the speed up and volley circuits, the operational latch, the sound and amplifier, coinage circuits, credit circuits, bonus logic, and the empty wall detector. And for now, let's just ignore the display, scoring, and spares. Yep, that's close, but don't let that number fool you. We still have a bit of surgery, so let's start a new column. We need everything in the oscillator circuit, so we'll just move that over. We need everything in the video counters, except this gate. The CET and CEP inputs already act as an AND gate, so we can just hook these up like so. And this matches the XY counters, as it should. My feeling is that this is an artifact from some experimenting and was just left that way. I tested this and it works just fine. In the sync section, I think this quad latch was added by Gary Waters to alleviate some of the glitch issues, so we'll pull that for now. Moving on, we can keep everything in the borders section. We'll even keep in those H-Sync suppression diodes found in later revisions. These don't affect the chip count, but do make the composite signal more compliant, so no harm here. For the paddle, let's remove circuitry for different paddle sizes first, and we can just use H-Sync for the paddle size counter clock since we just need to bump every line. No clue whether or not a tracked circuitry was in the prototype, but it's cheap, so we'll keep that in. We only have one player, so we don't need these gates or the 4016. We will need to bump that resistor up to compensate for the resistance drop in that analog switch, however. The early rev boards had some extra logic in here, but we'll just leave it like this. We'll keep everything in the ball XY counters, and you can see that they didn't have that extra AND gate. This is hooked up exactly how we did it in the video counters. In the ball motion controls, on the X motion side, we can get rid of the flip screen support. Then in the X counters, we can tie P0 down and P1 up. P2 then becomes a simple left-right signal at medium speed, and we can just hook that up to the X motion latch output. We're not generating this SBD line either. We're just waiting for the ball to be moving towards the player and not forcing it on serve. We no longer have synchronized signal, so we just need to relabel these. For Y motion, we can trash the upper latch, which varies the deflection angle depending on where the ball hits the paddle. Again, with the Y counters, we can tie P0 down and P1 up. P2 now becomes a simple up-down signal at medium speed. Let's simplify the wiring so the set and reset lines change direction when the ball hits the right-hand or left-hand side. Instead of checking if the ball hits V-Sync, we can just shove pad hit into the clock and use the PD line from the paddle counter to decide the simple reflection angle. Much simpler and reduces to just this logic. For the bricks, we can get rid of the FPD lines that come from the empty wall detector on data in and simplify the wiring. We can also get rid of the FPD lines in the right logic. Much cleaner. With only one player, we can just tie A7 down. We'll only be using half the brick storage. Not sure if this one hit at a time SR latch was in the original, but we'll leave it in there for now. We'll probably replace it with a 7474 instead since we have spare. The rest we need to keep. Well, this latch here was wired differently in the early boards, but we'll just leave it like this. We can get rid of a bunch of stuff in the start game controls, but we do need to keep a little. We can get rid of this inverter and just use the regular output from this latch. Yeah, but we still need to drive the start game line. Oh yeah, we also need to flip the tracked to the set side. Much better. We trashed the Q latch, but we can add a manual reset button here. One more gate reduction because we can bring over not EGL. This looks terrible, but reduces to this simple circuit with a chip count of only 1.66. Feel like I need a shower after that one. For the player up / ball and play circuit, we don't need the extra step generator for a single player game, and we can just drive the counter clock from the serve wait line. Here we can use a 7400 gate and readjust the weights to generate end of game when the counter hits 5. Note that with a single 2-input NAND gate, you can stop the game on any combination of 2 counter output highs like 3, 5, 6, 9, Able, and Charlie, but we'll leave it at 5. We can simplify the serve logic a little too. Here we can just check if the ball blows past the paddle and hits H-sync. This puts the system in the serve wait state. To get out of wait, we can just check when 128 Henry goes high when X2 is on. X2 is on when the ball is moving towards the player, and 128 Henry goes high when the ball reaches the near half of the screen. It should be good enough. Some of this circuit here was different in the early Rev boards, but we'll leave the rest alone. That's about as simple as we can get it. Naturally, I got stupid and built it. I couldn't figure out how to get the video counters working without delaying the load line by 1 clock. I was close, as you can see here, but got tired of working on it and wanted to move on, so I added a flip latch and a NAND gate back in to generate the delayed load. This plays just fine, and naturally it feels a lot like the production game because, well, production was based on the prototype, so yeah, that would feel close. Now this is only 35 chips, and you know Woz could have done the whole thing in 1 transistor, so we can deduce one of 2 things. There was more fancy stuff in the prototype, which is unlikely bonus-wise, or more likely, there was some kind of scoring. So at this point, we're going to assume there was scoring. The second question is, what type, on-screen or off-screen? No matter what, Woz would have needed 3 counters to accommodate a total possible score of 112, given 1 point for each brick. We can simplify the logic here to just 3 counters, still reset by start game, but now clocked by brick hit when not in attract mode. That's 3 1/4 chips to handle a score. Now if Woz used 7-segment displays, that would require 4 decoders, 3 for the points and 1 for the ball counter, assuming the ball counter was shown. So a nice LED display would bring the total of 42 chips. Still too low. I didn't feel like building out LED circuitry, but at least you can see the simple counter outputs on these displays. Next thing we should try is simplifying the on-screen display circuit. Let's start with a fresh screen layout chart, and I know you remember working on these. We only need 4 digits, and let's put them in a simple place. In the vertical space, we can just check that 128 Victor's off and 64 Victor's on, then use 32 Victor and 16 Victor to select the digit. In the horizontal space, we can check that 128 Henry and 64 Henry are off and that 32 Henry is on. We can still get a little fancy and have 16 Henry off for digit 3 and on for the rest, so our digits will sit visually in these 4 spaces. If you want, you can move this around a bit, like checking for 64 Victor be off and 128 Victor to be on, or check if 128 Victor and 64 Victor are off, but we'll leave it in the middle. Back on the schematic, since we only have 4 digits, we can begin by swapping out those 4 8-to-1 demultiplexers for just 2 dual 4-to-1s. For the ball in play digit, we'll keep the adder front end gates that convert the 0-based ball number lines into a 1-based on-screen digit. Anyway, we'll simply enable our 4-to-1 demultiplexers all the time. Then, since we want to enable the display only when 64 Victor and 32 Henry are on, we can AND them into the blanking input. The rest of the 7-segment decoder and segment selectors remain the same, but we can continue to simplify. We don't need the score flash timer and related gates. This was not present in early revisions. We can also remove the Player 2 stuff. Here we'll use a spare 3-input NOR gate from the other circuitry to block the display unless 128 Henry, 64 Henry, and 128 Victor are all off. We'll check when 32 Victor and 16 Victor are both on and shift the ball and play number up by flipping how we look at 16 Henry. Merge all of this using spare gates and voila! This should emit the on-screen digits. Well, we are now at 8.41 chips for the on-screen display, giving our version of the prototype 46 total chips with 1 spare inverter and 1 spare triple input AND gate. Pretty much in line with the WOZ count. I was originally planning to add the score and display circuits here, but realized that most of the required signals come from the video counters, so I built this section separately and stuck it over here. Turn that on, and nothing. Oops, that score line is not wireless. Helps to drop it onto the video bus. Now that's pretty cool. Feels strange having it in the middle of the screen, but it was cheap. Try that out. Works okay. Well, we've managed to build a working prototype with an on-screen display for just a biscuit over 45 chips. Since we're essentially in line with that 45 chip count, in my opinion, the original prototype had on-screen scoring. One last thought is that Gary Waters said that the original prototype came with a schematic on a single C-size sheet. I drew this up in KiCad. Yeah, the gates were probably different size, but there's no room on our reimagined one-sheeter for scoring logic. Maybe if you really cram stuff around. I added the scoring and display on a separate sheet. I will drop a PDF of this in GitHub for fun. Not planning on doing a circuit board for this, but I have been stupid plenty of times before. Alright, I think we've run down this rabbit hole long enough. If you have any insights, let us know. Thanks for watching.